Hello, everybody. It's nice to see you all. I'm just going to first show a few slides. I was asked to lead the discussion and also maybe make a few comments about the previous talks. So I think it was a very nice group of talks on STM measurements of a variety of different systems. And we've actually, a number of us, Berthold Younglong and I, have spent some time the last year being locked down, thinking about how we use STM to probe Majorana zero mode. And as you saw throughout the talks today, essentially the technique we're using is observing zero modes in the expected regime where we expect topological superconductivity. So this is all very nice, but one of the things that we've been kind of wondering about is what are the ways in which we can really distinguish Majorana zero modes from trivial ones. So I want to just spend a few minutes actually highlighting some of the work we did and others have done, which haven't, in theory, which hasn't led to experiments yet, which could apply to the systems that were just discussed, which might be worth discussing. And this has to do with spin selective measurements. Actually, quite early on from the nanowire work, actually from some of the work of people in the audience here, we already know that when we do tunneling to detect the zero bias mode of the Majorana in nanowires, the spin signal should actually be able to tell us, if you do spin selective tunneling, whether these zero modes have the proper spin orientation. So for example, here we see in one regime where the polarization is derived from the spin orbit coupling in a strong spin orbit coupling system of nanowires where you have a weak magnetic field, for example, inducing topological phase, and also all the way to thinking about examples that were earlier represented about vortex cores. These were experiments that were done which shows some contrast, which seems to be a distinguishing feature of Majorana zero mode. So I'm just going to flash some results which it's been done a number of years ago, which is on these atomic chain platforms where you have, in our case, iron chains on lead, and you detect with regular spectroscopy the zero modes that are temperature limited. But mostly I just want to highlight these spin polarized experiments that's kind of, I think, quite important when you do tunneling spectroscopy as a way of distinguishing Majorana zero mode. So for example, in our platform where you have the exchange interaction being much larger than the spin orbit coupling, here are chains in which you have magnetism from magnetic ions, and then you have spin orbit coupling from the superconductor. You have the Majorana inherits its spin polarization from the underlying band. This picture actually is quite similar in the Rashba nanowire case, except there the spins, instead of being kind of dominated by the Zeeman term, are dominated by the spin orbit coupling term. And so one of the experiments which we thought about doing, which we did in 2017, was to use spin polarized STM. And actually, the signature of in-gap states that are trivial and the signatures of in-gap states that are Majoranas are actually distinct in the spin polarized STM measurement. It has to do with the fact that the spin polarization of in-gap states basically derive, as it was shown in the theory paper, from the spin polarization of the normal state. And when you do spin polarized STM experiment, by the virtue of the fact that you have a feedback loop that controls your STM junction, you get this very characteristic asymmetric behavior for in-gap states that are trivial. And this feature basically cancels whatever polarization you get for Majorana zero mode. In fact, when we did these experiments on atomic chains, when we are at the end of the chains where we see the zero bias peak associated with the Majorana zero mode there, we see a very large spin contrast that when you calculate the polarization, you can distinguish that spin contrast from that of the trivial in-gap states that appear at other energies, which not only exist at the end of the chain, but also exist, of course, inside the bulk of the chain of these magnetic ions. This asymmetric feature is a characteristic of these in-gap states. So this is something that can be used as a diagnostic tool. We use this in the atomic chain experiments, and more recently, where we looked at the topological edge states of bismuth, where we induce superconductivity with the substrate and magnetism with iron clusters, where we also detected signatures of zero modes at the interface between this magnetic and superconducting gap region. This is the Fu and Kane proposal. Even there, we also see when we do this spin polarized measurement, we can distinguish the zero mode that's induced by at the boundary between these two phases have a spin polarization that's very different by the in-gap states introduced by, for example, magnetic defects. So just lastly, I want to say that we heard a lot about iron-based superconductors earlier. And here's an example of application of this technique by the group in Hamburg, where they were using the STM to look at impurity-induced states by what was, I guess, reported to be maybe iron defects on top of iron selenide, which produced this very sharp zero energy state, which was actually initially thought to be maybe due to Majorana states. It also lives very sharply near this defect. And what they found is that using this spin polarized technique, they could see no contrast for this zero bias peak, basically showing that most likely this is a trivial mode. So I'm almost to the end of my comments here. And what I would like to do is just open the floor for a discussion. I have some comments that I've put on to spare on the discussion, but let me see if I can bring on the chat. If there are questions about what I said, please feel free to ask now, and then we can delve into discussing all the different talks. So maybe I ask you if you have any questions. So let me see if I can see the chat. I can't see the chat. Well, can you see the chat?
Sorry, I was muted. I can see the chat. There are no additional questions to your talk.
Okay, excellent. So
everything was extremely clear.
Okay.
Oh, there is. Carsten. Please ask Carsten.
Please go ahead.
Yeah. Hi, Ali.
Hi.
Hi, can you hear me?
Yeah.
Good. Yeah, so you're saying that you can distinguish Majorana zero modes from other modes by the spin polarization?
From the Shiba states, yes.
Yes, and I agree that they will have distinct features, but not exclusively, right? But you can probably cook up an Andreev bound state that could look similar or have similar spin physics.
So, for example, in the
zero energy, I mean, not a finite energy, but zero energy.
Right. So, in the case of when you're looking at these atomic scale system, to get an Andreev state, you need very smooth variation of the background gap, right?
Okay, to have them, you mean?
To have them, which
yes.
you can see if those states exist there with your STM. I think that one is easy to distinguish if there is some state living on the length scale of coherence rate. I agree with that. But mostly our purpose is to try to distinguish between these more localized Shiba states, which are living they could be living trivially at the end of any of these systems that were discussed today. They're not Andreev states in the sense of what you have in the nanowires. But that's a good question. I don't know whether what I do know is there were these proposals early on about spin polarization in nanowires. I don't know to what extent they are robust. Are you saying that they're not? Because, for example, their spin orientation is very specific, right?
I'm just saying that you cannot distinguish, but you can build up confidence.
Okay.
But you cannot exclude other kinds of, accidental modes that might have similar physics and accidental Andreev modes.
Yeah, I think that's in the case of the Shiva states, it seems like we have some good examples. Now, maybe we find cases where it would be very contrived. That would be interesting to see as well, what are required for them and how would we look in the experiments. Good.
Adi had a question. Adi, please.
In some sense, following on Carsten, did you think of situations where there are several Majorana modes at the end because you have a 1D system that's not class D but class BD1 and the topological index may have may have any integer value. For example, if you have a multi-band 1D wire. So in this situation, would that there have to be a spin signal or?
So I think the way I think about it is in what you're describing, Adi, is like, let's say if you have mirror symmetry, right? If you have perfect mirror symmetry, then you would have two Majoranas, but they are derived from the original spin polarized band. So I think that they would have similar spins, but they will have different, they have different mirror index, I presume. And I think the same test may apply, but I don't know if anybody's looked at that.
I see, but you think that that they would show the same signal as a single Majorana?
I think you couldn't distinguish whether you have two or one if you have this perfect symmetry. I don't see how you could.
Okay, thanks.
Yeah, there is a comment from Hong Ling.
Yes, Hong Ling, maybe unmute yourself. Yes.
Yes, I'm still here. I have
Excellent.
a comment on the impurity state on the iron-based superconductor. We had we have done some work on the similar system, on the same system. In fact, Dongfeng Wang is the first author for our first science paper, and then he moved on to German. So we did a similar experiment, and not for the spin resolve, but for the regular one. We identified two types of bound state. One is U-Shiba state. And some U-Shiba state will stay at 0. And then, of course, if you use a spin polarized tube to look at those U-Shiba state, you will not see a spin polarization. So we strongly suspect, we actually discussed with them, with Dongfeng, and he seems to agree. So, but also there's some type of true zero mode, and which will not split on the magnetic field. That we believe is possibly a Majorana zero mode for the so-called the quantum anomalous vortex.
Yeah, I think
we're not so
interpretation.
Yeah,
so do you have any spin polarized measurement on those states?
No, we haven't done that. We haven't achieved spin polarized way in our STM. So, but I will come back to the vortex bound state, which is not physical defects. So in that case, we think we are pretty sure that's a real Majorana zero model, given the very large level spacing, and clearly see all of the index, all of this angular momentum level, and so that's why we're calling for yes.
Yeah, so I have some questions for you on that comment, but I see that we have a raised hand. And Elsa, can you unmute yourself? And then
yes. Hi, everybody. So just I didn't get very clearly what is exactly the different signal you get concerning the spin polarization of these Shiva states with respect to the Majorana.
Yeah, very good. Okay, so let me explain that. So when you have a Shiva state, they appear in pairs, right? At plus and minus.
Yes.
And they could be trivially go to zero energy. And this could look just like a Majorana. And you have basically both electron hole, okay? Now, if you look at what the spin polarization looks like relative to the normal state, okay? When you have a state that's appearing above the chemical potential and one below the chemical potential, one would have above the normal state spin polarization and one would have below the normal state polarization that's created by the impurity to give you the in-gap state. And then, but when it appears at zero, this polarization would be exactly, equal to the normal state background. So if you're able to measure the spin polarization relative to the background, a Shiba state will have exactly the spin polarization of the background. But the Majorana is a very different beast because it comes from that band that you cut, and your spin polarization comes from that band crossing.
Okay. Yeah, so I agree. So I think the problem with the Majorana states that are trivial, these quasi-Majoranas and so on, is that you have states at zero energy that have a partial overlap. And when you calculate there the spin polarization, you can see that it's fairly similar to what you would have with...
about two Majoranas that talk to one another that become split.
Yes, well, no. But these Majoranas, they really talk one with the other, but in energy, they don't become split if there is a smooth confinement. So they can be perfectly at zero energy, but you can have a partial overlap. Actually, it can be very much overlapping in space, but not in energy, So the question is that I agree with you when you have two such states exactly at zero energy and perfectly overlapped, like you would have with a Shiba state, if I understand correctly, then I agree that the polarization of one of them could cancel the other. But what I want to warn is that you might have also a zero state with partial separation and get a signal, a different signal for these two components in the polarization, and you might think that therefore is a Majorana state, but still it might be very much overlapping in space. This is something we have calculated in one of our papers.
Because what we see is the polarization of the Majorana is larger than the Shiba states that we get in the bulk of the wire, which is very unusual.
Okay, so it's a question of magnitude. In general, the way to really see this, I would need to see both Majoranas and check that one of them has a sign and the other has the opposite canting of the polarization. That would
actually very true. I think that this canting is one of the key signatures that makes this
exactly.
Yes.
Yeah, and then you can see actually the spin polarization all along the bound state
You make a very good point. We have some signatures of this in our measurement, but because it's dominated by the Zeeman term, this signal is very small.
Yeah, that I agree. So you have it's dominated by the Zeeman field, but then there is a canting with the spin-orbit coupling in one and the other direction, depending on the left and right Majorana.
In states of bismuth, we found this contrast to be actually very large. That the zero mode spin signature was in a different signal than it was of the magnetic induced states. That actually there is much bigger because the spin orbit term is more dominant than in the
Okay, thank you.
Let's see if I don't want to keep Hang Ding up too long, but
come back to your list of comments.
I have a provocative question for you. So what if you have this in-gap state that's coming from defects and it's at zero energy and the vortices just love to sit on defects and would just sit on the defect state, and this is zero bias peak. It's true zero bias peak, and it's coming from a Dirac band structure. So it would sit at zero, and it will have some of your angular momentum properties, but it's actually the physics of it has to do with the impurity state. Is that at all possible?
It's very unlikely. Yeah, very unlikely, because I have two reasons. First of all, we check the zero field, and we don't see the impurity. Okay, that's one point. Secondly, we check all the parameters. So because we not only see the zero mode. We also see the other higher order, ±1, ±2, 3. So all of this can agree. So with a single Dirac cone, with the known superconducting gap and known Fermi energy. And so this cannot be an impurity. Impurity, you cannot have this. So that's yeah, the extent to have this is highly unlikely. Of course, if we can tune, suppose we can tune the chemical potential by hand, say by apply pressure, and we know, and then we can tune, by tuning this, we can also tune in the Majorana zero mode in and out, and also tuning the level spacing accordingly. Then we think that it's very difficult to refuse, say this is not, this is a Majorana zero mode. So that's yeah, my opinion.
All right. Let's see if there are, we have still a good number of people here, haven't bailed out yet. So let's see, other questions, comments.
Well, you point a few interesting questions here. Maybe people from the audience can try to answer that.
So actually, can I expand on Ali's question and come back to Hong Din's to discussion there was there? Should there be an edge mode at the transition from topological to trivial?
Yeah.
So Hong Ding, you said that there shouldn't. Could you explain that?
Well, it's not a true topological superconductor. And I believe in Liang Fu's paper, he pointed out so that in a true topological superconductor, either the boundary to the non-topological phase, that you will have this the mode, but in this case you are not.
But
yeah.
If you have a single Majorana mode inside the vortex, then I think that
yes.
there must be a gapless mode
at the
edges, because there must be a total even number of zero modes, and if there's a single vortex,
sure,
it would carry a single Majorana. There must be another
yes.
one. It would be on the edge.
Yeah.
And so, in what way? So, how does this argument relate to your system?
No, we think we have this two surface, so we have a pair, one on top of one bottom. But in your case, if you have the single one and that you have an island inside the island, if you have only a single Majorana mode, of course the others will be on the edge. Yeah, I agree. But that's not our case.
Okay, I think we have a question from Abe.
Hi. So my question is related to the Majorana zero bias peak in the vortex core. I'm trying to think what would be its response if we apply an in-plane magnetic field small enough that it does not break superconductivity, but could it still gap out the Dirac point and have a different response on the inside the vortex core?
If the field is large enough, of course, they will gap out this Dirac cone. And if it's large, if the effect near EF, we will not see Majorana zero mode. Yeah.
But the magnetic to gap out the Dirac points, you need to have the field, right? It's in 2D is pretty large, right?
Very large, yes.
But here it's we are talking about the 2D surface, but the system is still 3D, right? The FASCTE system.
Yes, but here what we see most from the 2D. So you can think of just use this. Of course, the full calculation you have to take a 3D, and people have done that. But to simplify it, it's similar to the 2D, like a Liang Fu's case, and so the 3D only change some parameters. Yeah, people have done the calculation on 3D case.
Nice, thank you.
Okay.
Sure.
Okay.
So I guess I had one question for Mogera. So you said that there are five modes underneath in your gold nanowires, 5 transverse modes. I don't know if he's still there or he left.
Well.
No, sorry, I'm here.
Okay.
Yeah.
Okay. So yes, there are 5 modes according to the estimation by the model by Patrick's group. So for the kind of nanowire,
you know the chemical. So your chemical potential has to be. Yeah, I'm just trying to get the picture. Like you have 5 1D modes, and your chemical potential has to. What's the separation between these modes in energy?
That I do not know. What's the energy separation?
But you have to hit the odd number of them, right?
Yeah, right. It has to be a hard number.
It's otherwise it's very unlikely, right?
Yeah.
Mm-hmm.
It's about the 30 milli-electron volt from the band bottom, from the surface band bottom.
So presumably, if you change the thickness of your europium sulfide, you can change the amount of the band tuning that you get from the charge transfer.
Yeah. So for example, as you saw, 0.9 monolayer, it's about 200 milli-electron volt shifts by, whereas if you go to 2 monolayers, it shifts already by basically almost 400 milli-electron volt, 450 milli-electron volt. After that, it doesn't make much difference.
Okay. I guess I had one question for Abe for their 2D superconductor.
Ali, I think we also want a short break between the 2 sessions. So
don't we have 2 minutes? 1 minute now.
No, we have still 10 minutes. So okay. Go on.
So do you?
No, ask this important question. I know what. Go on. Yeah.
Of the sample, do you see in-gap states?
Sorry, could you please repeat?
If you have a defect in the middle of your sample, do you see in-gap states?
Yes, we do see in-gap states, and it mostly appears. We don't see it as a discrete state like YSR state within the gap, but we do see that the gap kind of becomes a bit asymmetric, the superconducting gap. It's as if we had a state and it got thermally broadened.
Like it's at the edge of the gap or something.
Right. And that actually we see that it's clearly distinguishable from the what we see on the edges of the step edge.
Okay. Are there other questions? Raised hands.
I had a question about to Jagdish actually. So when you say you have these 5 transverse modes underneath the europium sulfur that is calculated, would it be possible for the STM to measure these as Van Hoff singularities if you sit on top of europium sulfur, or is it true underneath the transverse modes? I can't hear.
You're muted, or you're still thinking.
No. Okay, sorry. If you want to see just underneath the europium sulfide, very edge, it's very hard because we don't have enough resolution. Unless, of course, you go to much lower temperature. Our temperature is also limited to 360 K millikelvin. So it's possible if you go to very low temperature, a little bit higher field, you may be able to resolve these things. That answers probably Ali's question also for the energy difference between the different modes.
Okay, I think we are officially, we are officially out of time. So I'd like to thank you for sticking around. I guess we have 10-minute break before we come back.
Yeah, 10-minute break. And thank for all the speakers of this session and to the discussion leader, and see you in 10 minutes.
Thank you.